Hello, good evening to all. So today in this course, okay. So today we'll try to solve the homework two questions. So the first question is, I know that you all have the assignment. So I am just reading the questions from the assignment, and that you can also see. You will be able to see from the video. So yeah. So the first question is explain flux quantization in a multiply connected superconductor. Just for superconductor, I'm writing S. Now, what is flux quantization? So flux quantization occurs due to wave function single valued nature, right? In a superconducting loop. And multiplied connected superconductor means a superconducting ring in which there is a hole, right? And through that hole only the flux lines can penetrate. Now there is a catch that for the multiply connected superconductor, only the since the flux lines are penetrating through the hole, and these fluxes take values which are only quantized, means only the integer values. Whereas for simply connected superconductors, they can take like any value, and also for simply connected ones, they can shrink to zero and all also. I'll just write these things down. So in a simple diagram I'm writing, let's say this is a simply connected superconductor, and this is a multiply connected superconductor, and there is a hole. If this simply connected, the whole thing is superconducting, then for the multiply connected superconductor, except the hole, other thing is superconducting. Now, through this hole, flux lines can penetrate and take values only the quantized ones, right? Like one quantum, three quantum, four quantum, etc. Only the integer values. Integer, integer values. Okay. Not the half ones, half like that. No. Now for simply connected the superconductors, this flux quantization holds through the like the contour is in every corner of this area. But for this one, there is a one specific area allotted for the superconducting. And for normal one, the contour can shrinks also. It can shrink to zero, right? But for the multiply connected one, it's not possible. Okay, so this was the first question. Then the second question is write down the BCS Hamiltonian. Okay, for the first one, we can also do more. So the first one, like this is the basic concept, right? Now, If we want to write that London equation and the Landau theory, now on that principle, sorry, on that principle, the supercurrent flows in the ring, right? Now, superconducting wave function, we can also write it as psi of and e to the power I theta. Theta means the phase. Now, supercurrent also can be written as E by M square cos square dag theta minus E. Right, where this is the vector potential. Now, if we integrate the loop using the Stokes theorem, then what will it be? Here we can write. We are integrating, right? So it will be around 2 pi n by h cross. Now means here n is the just the integer, right? That is coming due to the single valued nature of the wave function that I just told. What is multiply connected superconductor in terms of flux quantization. Now the magnetic flux quantum will be phi, or writing just magnetic flux quantum is into this, right? That means n into h by 2e. So here this means the flux quantum, or you can also write it as phi 0. This means the flux is quantized in certain integer values of the phi 0. Okay, moving to the next question. BCS Hamiltonian. So BCS Hamiltonian, in the question there is something given. No, just write down the BCS Hamiltonian. Okay. So it's basically H. Sorry, something happened. Let me check whether it's recording or not. Yeah. So we were on the flux quantization. So since maybe there's a problem happening, just give me a second. I don't know why this is happening. Yeah, so we are on the BCS Hamiltonian. So I'm just writing down the BCS Hamiltonian. You can also find it in Sir's lecture. So it's nothing, just, yeah. This is a BCS Hamiltonian. Now we have to just understand the terms, right? Now here, CK, this CK and CK dagger plus, this is the creation and annihilation operators for an electron with wave vector K, right? K is in the subscript. Now, this, okay, I'll just write, is a creation and annihilation operators. Now, the K is the energy of free electron measured from the Fermi level, right? I'll write it. Measured from Fermi level. We can also, there is the term, it's already given. Okay, now mu is the chemical potential, right? And going back to the, if I'm right, if I write this as a equation one, then in the equation one there is one term is Vk K prime. This is the interaction potential between the electrons. Since you already know the in the superconductors there are interaction happens in between electrons, not like the, like it doesn't obey the Pauli exclusion principle. Interaction potential between electrons. Now, the other terms, they represent the Cooper pair formation when where two electrons with opposite momenta and spin uh, mm, bound, like form pairs, right? So this is basically terms when uh, two electrons with opposite momenta and spin, up spin, down spin, interact each other or uh, make Cooper pair. Okay. So this BCCS theory, this tells that there is an active interaction, like leading to Cooper pair formation, and this is due to like rise of an energy gap, which ultimately leads to the superconductivity. Now, this next part is compute. To B question is compute the expectations values of the kinetic and potential energies for problem 2, yeah, in terms of the coherence vectors UK and VK. Now, to compute the expectation values, we need to take the help of the this theory, Bogoliubov transformation. These are the basically, this tells us the quasi-particle operators, right? Whereas alpha k is the mu k, ck for upspin, and vk c minus k down. Then the same thing with the opposite case. Right. Now here the you can VK already mentioned in the question, there are the coherence fact. This is coherence factors. And since they are the coherence factor, they should like satisfy the normalization condition, which is uk square plus vk square equals to 1. Right. Now from BCS theory, we also know that uk square is equals to half of 1 plus z k by e, and vk is the similar thing, vk square, just with a negative sign. Right. So here this z term, it is, you can write it like this. This is the energy of an electron relative to the, like comparing to the Fermi level. And also E K, the energy, this is a quasi-particles energy, right? Where del is the energy gap. And using these expressions combinedly, the expectation value of the kinetic energy will be summation of K. It is K by Vk square, and the this is for kinetic energy. And now for the potential energy, the expectation values of the potential energy will be minus with the minus sign, the summation of del uk into vk. So this is the fundamental in deriving the total energy of the superconducting state. Anything else they have needed? Compared to, no, this two terms only. So this will be the two terms. Now, the C question is, convert the total energy of B, okay, in terms of a single variable, namely theta k, such that the coherence vectors are uk vk equals to sine theta k. Okay, uk is sine theta k and vk is cos theta k. Okay, they have given this, and the total energy, we have to detect the total energy in terms of some function of theta k. Okay, so E we can write 2 of, means basically, okay, I'll just write separately. E equals to should be T plus the kinetic plus potential energy, right? Now taking those two terms, okay, summation of zeta k vk square, right? Okay, I'll first write in vk uk's term, vk square minus this, that minus sign, del uk uh, vk, right? So just putting the values of the uk and vk, cos square theta minus del of sine theta cos theta. Right, now minimizing, they have asked to minimize the condition. Sorry, just a sec. Now minimize the energy with respect to theta k. Means we have to do the derivative, right? dE by d theta, it should be, now uh, for cos square theta we have to do like derivation with respect to theta. So it will be just be minus 2 sine theta cos theta minus of del. Now for sine theta and cos theta separately we have to do no cos square theta minus sine square theta. Now this minimizing condition is this should be 0. Now if we simplify everything, then it will be del pi. I'm just skipping a few steps and finally you will get this. Okay. So yeah. So now the this gap equation, BCS gap equation will be del equals to V into K summation over K del pi 2 EK tan inverse EK 2 KB T. Okay. So this will be the equation. You just if you solve in more steps, then you'll get, of course. Now, what do you know? What we will get? We are getting to know from this equation. Basically, this equation tells us that the uh, determination of this del, the superconducting energy gap, it's quite self-consistent, right? Uh, so the interaction strength V and the density of the states of the Fermi level, that is the N, control the magnitude of the energy gap means V. V is what? The interaction strength. And there is one more term, N, in terms of Fermi energy, means this is basically density of states. Density of states at Fermi level. So this too determines the magnitude of energy gap. Now, yeah. So if you want to do it in lower temperature at zero temperature, from here also you can do. Okay, but that's not in the question, so we want to go there. So the next question is find an equation, find an expression for the energy gap del with reference to the Fermi energy in a superconductor for an attractive potential between the electrons of the form it's given minus V naught for all K and K prime, they are lying in between H plus omega D to G of the F. Right. Now here, this one is basically D by energy. And this one is the interaction strength, just now I told. Now we have to solve the two particle Schrodinger equation. Yeah, it's because it's asked in the question that we have to solve the two particle Schrodinger equation for a single state wave function to arrive at the result and assume that the electronic density of states is predominantly from the contribution at the Fermi surface. Okay, we'll try to resolve that. Now, for a pair of interacting electrons, the Schrodinger equation is right. So for our given potential, this is given, right? It's this whole thing is given. This tells that just putting the value whatever is given in the question. Yeah. Now defining the gap. This is the gap equation, right? Now, for a constant interaction of V0 within this is given, right? Within this d by energy cutoff, this gap equation will simplify that. Just putting this value. This is already done in the last question. So EK, you already know the quasi-particle energy. And at t equals to 0, we can write EK is root over of ck square plus del square. Now we have to like evaluate it over the sum over the states, right? Now the density of states. So density of states we write it as like this, right? Now the gap equation. And one more thing is that summation over this means it will be in zero from, as it is mentioned in the question, it will be this barrier, right? And yeah, d. Now the gap equation will be del is will be the one, right? So I can take it as one. Now v0 n 0 minus h naught d plus h naught d divided by 2 into is it a k square plus del square. Just putting the values. Now this one you already know. Okay, this happens to be this tan inverse ek to the divided by 2 kVt. Or I'll just write, means what I'm trying to tell is mm, or I'll just further write, right? This I have already written. So taking this in the equation, it will become this is del, this is d. And rearranging, you just rearrange that, then del will be sine of V0 1 by V0 n 0. Yeah. So this shows that the superconducting energy gap is very much lesser, and it has been it we can call it as a weak coupling, right? And anything more asked in the question? Mm, assume that the electronic density of from the contribution of the Fermi state. Right, we have already included that, so nothing more has been asked. Now the fourth question is, consider pairing of electrons mediated via phonons. Okay, so draw Feynman diagrams, if you remember, of two processes in which electron, okay, we'll just first draw the two processes. So in which an electron with momentum of k releases a phonon with momentum q, which is later reabsorbed by another electron with momentum minus k, and in other electron with minus k releases phonon, which is later reabsorbed by the electron with plus k. Okay, this is very much evident and in the like course. Sir has already drawn this type of things. So what is happening? K is getting absorbed and releases with a photon with a momentum of k plus q, and minus k is getting absorbed, and similarly it's also getting released, right? So yeah. Mm, so this is the thing, and the second process, this will be the q1. Right. And they have asked that identify the initial, intermediate, and final state energies. Then the initial energy, if we write EI, it would be 2 of this K. When the phonon is K, right? And for this process, the same thing. The same thing as this. Now for the final energy, or EF, we can write to be the 2 equals prime, and it is the same for this one, and where I'll just write here ek is the h, h square k square divided by 2m minus mu, right? And for the intermediate state, intermediate energy, E int, we can write it is the this two summation and h omega q. This is also energy term, right? Means h nu basically into Planck's constant into frequency. Now for this process, if this is A process, this is B process. Now for this one, it will be E into A, E into B, into for intermediate. This is the summation of this two plus h omega d. Okay. Now that moving to the fifth question, or is there something? Okay. Show that this process under certain conditions yield attractive interaction between the electrons. Okay. So this we can write as, since this is already all are phonon mediated, so no problem. If we solve this, so it will be right. So the question was asked. Okay, show that this process under certain conditions yield attractive interaction between the electrons. So we have shown the electron interaction from the initial to final stage, and like taking the intermediate, of course. So if we try to draw the potential, right? This is for omega term, of course. So this is the relevant regime where the potential will be attractive. Now the fifth question is show that the electronic specific heat of a superconducting state is given by some equation is there, and now where the terms are also given. Okay, so we'll just quickly first write down the equation whatever is given. This is given, and they have also given ek equals to this. This has we have already used earlier. If k is this, del t is 1.74, del 0 1 minus t by tc to the power half. Right. So yeah. Now you all know that the specific heat in a normal metal which is in without a superconducting condition, it will be 2 pi square by 3 n of this Fermi energy kBt k square t. Now, this is the density of states at the Fermi level. Kb is the Boltzmann constant, T is the temperature, right? Now, in a superconducting state, the heat capacity changes due to the opening of the energy gap, that is the del T, and that alters later in the electronic energy levels. Okay. Now, electronic energy, we have to understand the electronic energy in the superconducting state. Now, the total electronic energy in the superconducting state, it can be given by this, right? Where Fk is the Fermi-Dirac equation, not equation, function. Fermi-Dirac function also Fk, we can write it as e to the power beta Ek plus 1. And Ek, you all know, many times we have like taken this equation previously. This is the energy of the quasi-particles in a superconducting state, right? Now, using this mechanics, the specific heat is obtained from the temperature, like temperature derivative of energy, right? Normal. C equals to d by dt. Now, we have to differentiate this one. Means we have to differentiate this. Let's say this is the energy of the superconducting state, right? And this is the temperature. And this is also ES, right? Like in the superconducting, under superconducting temperature, this term only. Just the multiplication will be bifurcated, right? Like one term at a time, derivation. Yeah. Now, this Fermi function, if we like do the derivation of this, we can write it like this also, right? Now, this term can be written as, right? This means 1 minus Fk. Means B is basically 1 by kBt. Beta is equal to 1 by kBt. Then we'll get dfk by dt is minus beta fk 1 minus fk de dt, right? Taking from this equation. Now the temperature dependence of this energy gap, it is given 1.74 del 0. It's given 1.74 del 0 1 minus t by tc square. 1 minus t by tc to the power half. This is given, right? Now we can also write it as del 0 minus 1.74 del 0 into t by tc to the power half. Then, like derivating it with respect to temperature, it will be, since the first term will be 0 by 2tc t by tc to the power minus half. Right. Now EK is already given, and okay, from EK also we can do that. This is given, right? Now derivating this also, a lot of derivation you have to do in this course, into d del by dt, right? Now substituting everything, whatever we have gotten till now, in this CES expression, which is what is given, already given in the question. So I'll just write first the equation given in the question. CES, or I'll just copy from me. It's not getting copied. Okay, I'm writing this down. CES equals to minus 2 by T K D K D E K E K square plus half beta D of del square divided by d beta, right? This is only. So we got the values of this one, this one. This actually basically this term is the temperature dependence. You can already can see temperature dependence of the energy gap, and this term comes from the differentiating the total energy, right? And you can also so basically this expression shows that the superconducting energy gap it depends on the electronic specific heat, right, which is not the dependence in the normal state. Like in normal state, if this is there, there is no dependence of the on the electronic specific heat of the total heat. Yeah, that was the question only. So basically the question was this only. Okay, this will be this. Like they had to show, they asked you to show the electronic specific heat of a superconducting state is dependent on not. Yeah. So this will be this only. See, yes, we have just proved it. Now, uh, if we want to like look into the physical interpretation, we can tell that when at low temperature the specific heat it should decrease at and it can go to zero, right? So this is because the quasi particles are thermally excited only above the energy gap, and when the T is almost Tc, when the T is almost Tc, means the first term I told, when this is lesser than Tc, then the specific heat will be going to zero, right? Because above a certain del value only the quasi-particles gets excited, and that will eventually contribute to the CES. Right now, when T is almost equals to Tc or the critical temperature, this del T, this will 1 minus 1 0 means del T will be 0, right? So then the specific heat shows a jump, a sharp jump, right? This jump is experimentally observed and also known as the like the main criteria for the superconductivity. Now, when P equals to Tc, this difference, the difference between the superconducting and normal specific heat, well, C divided by C in Tc, this is one the value 1.43, right? So basically, what we got to know from this question, we are getting to know that the electronic specific heat CES in a superconductor is derived from the temperature dependence of this electronic part of the total quasi-particle energy. Right. Now the Fermi equation, the Fermi function and energy gap variation, it's important for the CES, and also the BCS model predicts a sharp jump of the specific heat. Now, regarding this jump only, there is one question in the next question, which is calculate the jump in specific heat, and del C is given as CES minus CEN at when T equals to Tc, right? For Q5 already given. Express your answer in terms of N, E, F, KB, and TC. Right. Now the CEN term, this specific it at the for the normal state. I have also written it previously. This we write it as, here we have written, no, right? This one. This is N is basically the density of states. Now, using the BCS model, the ratio of the specific heat will be del C by C and T. If we divide this both, it is around 1.43. It is basically a experimentally valid result. Okay, so you don't need to worry about that. Now, the for the homework 2 question is done. Now I am adding one more question, and the question is, I'll just I'll just write the question and I'll also solve that. Now, question is, consider a Hamiltonian. Okay, maybe you are not you are not expecting this question, but you can write it down if you want to when there will be the this video or the lecture will be uploaded. Okay, now this is the Hamiltonian. Now compute the expectation value of this value of between the BCS states spin down spin. Yeah, where is a normalized field pharmacy using UK equals to sine theta k, VK equals to cos theta k. Express the results of this part, okay, using this. Redefine result of A. Now the third question is minimize. The same thing we have to do. With respect to theta, and D is obtain an expression for the gap function del K. So this is the question. Okay. So this problem is basically we have to compute the expectation value of this Hamiltonian H means mu n in the superconducting state, and we have to also minimize it by derivation, right? By deriving the by means derivating the BCS gap equation, right? Now the Hamiltonian is given here. Here, this one, this one. Now here we can say that this term is already been discussed earlier. So this is the energy of an electron relative to the chemical potential, right? Now these terms are given. These are the fermionic creation and annihilation operators. V term is also given, right? Vk. So this is the interaction potential between electrons. Now the BCS state wave function is also given, right? Where this you can we get the BCS coherence factor has already been discussed earlier, and this term, this is the field pharmacy already mentioned in the question, where all of course all states below the nu are occupied. Now we need to compute the expectation value. How can we write the expectation value? What will be the expression? Expectation value, we write it like this. Right. Now to calculate this term, we need one kinetic energy term, right, and interaction energy term. So the kinetic energy term of this, it will be the kinetic energy term. So here, you already know that V square. This is basically the probability of occupation, right? So also can be written as and there is one interaction energy term. This interaction energy can contribute like this. This down. Then Cl, it would be down, Cl up, and then side pieces. Right. Now using the BCS gap equation, the del is UK, UL, not K, UL, VL, right? And the expectation value, hence the expectation value of the interaction energy, it will be right. Now the total energy expectation value will be this is won't be L, just this. VK square minus del K UK VK. Okay. This is the total one. Now expressing the terms in terms of theta. Now theta we already know how we describe it. U equals to sine theta and V is cos theta. Now the same thing I'll write. Now this third question is asked minimizing with respect to theta. Just do this minimization d by d theta. Now minimization will mean that this means 0, right? Now, you already know, though I have done previously, I'll also do one more time. Cos square theta, it will be minus 2 sine theta cos theta, and d by d theta of sine theta cos theta, it is basically cos square theta, means taking one derivative at a time, minus sine square theta. Okay, I'm just putting the value here. Sine theta cos theta minus of del, this is cos square theta minus sine square theta. This is equals to 0. Right. Then you can write it as del into cos square theta minus sine square theta equals to 2 zeta k sine theta k cos theta. Right. Hence, also you know that this is the expression cos square theta minus sine square theta divided by cos theta sine theta equals to cot 2 theta. Okay, so if we do that, it will be del k into cot 2 theta, or I'll just write it freshly from here, del k by 2 into cos square theta minus sine square theta divided by sine theta cos theta is equals to this. Right. Hence, del suffix k by 2 into cot 2 theta equals to this. Then cot 2 theta means tan 2 theta will be the opposite one. Means if you do the 1 by thing, it will be, means if we take the cot theta here, del k by 2 into theta k. So this is the expression we got. Now, another question is obtain the expression for the gap function del k. Now the gap function del k, it is expressed by VKL UL VL. Right. Now we have to do the same thing in substituting U as in sine theta and V as in cos theta. For this case, it will be if we do multiply and divide simultaneously with 2, it will be 2 sine theta cos theta means sine 2 theta, right? Summation of VKL sine 2 theta. Now, substituting the sine 2 theta, is where EK is this. Del K will get VKL del K by EK. Okay. Now the same thing. We'll just rearrange these things and we'll get if we can think of this one, VKL is almost equals to V for small energy difference. Then del will be V of del Tk. Okay, which is the basically the BCS gap equation. Okay, so this one is needed only, I guess, obtain the expression for the gap equation del K. So this is the final equation. Okay, and the third, I can see that the fourth week content is already uploaded. Fourth week content is already uploaded, and the third week content, the assignment is due, I guess, tomorrow for tomorrow. For tomorrow. So once the due date is over, actually we should not reveal the answers for. So I'll solve the third week assignment, third assignment in the next class, and fourth assignment also I'll pick because third assignment, yeah, we can do that. We'll do that. Fourth assignment, there are 5 questions, and in third weeks, you have 10 questions. Okay. If we can't do, then we'll do one extra class and we'll solve the each and every question. And the fourth assignment is due up to 19th. Okay. And we'll be having our next class on 18th. Okay. Then it will be beneficial for the fourth assignment submission. I hope you all are submitting on time. Okay. So yeah. Today's class, I guess we can end it here. There's too much we have done today. So I'll share this. You can go through the portal and have this PDF and also the YouTube link. You can click and you can have the YouTube video. Okay. All right, then I'll take the leave. Thank you for joining. Just हुआ तीन बास्केट वाला आया हुआ है जब मैं ऑर्डर दे रहा हूँ क्या ऑर्डर किए कुछ नहीं जल्दी से लेके आ जाओ वो 1 घंटा से कौन कर रहा है तो उसको तो उसकी गलती है वो क्यों इतना लेट आया क्या वो निकलने वाला है तो अगर लेना तो लो नहीं तो फिर एक मैंने जस्ट कट किया कॉल मैं आ जाती हूँ अभी 2 मिनट में उसको कॉल करके बोलो कि भैया 2 मिनट रुको और मैं 3 मिनट ठीक है फिर मैं बोल देता हूँ